Okay, so this is part 5. The last time we were working on our live demo, we had entered most all of the parameters, and we'd calculated borehole thermal resistance. So we're actually ready to size this. Okay, and I've picked 90. We'll stick with the 90. Let's see, this is far too low, but probably anything we hit, so maybe let's just put 45. Don't think we'll hit this. And right now we start in the first month 1, last month let's do 20 years. You can actually start in a different month from 1. So for example, some buildings that are cooling dominated, if you start operating the system in January, it may be that the first winter you'll actually have the lowest temperature. And it might be that you even end up sizing to meet that peak in the first winter. Right? Well, that could happen if you start operation on January 1st, but if you're going to start another in a different month, it might be better to use a different first month of the simulation if you're running into this problem where you're showing that the maximum temperature occurs in the first year. Okay, we can also choose to create a CSV file, which is very handy if we want to plot this. And we'll write this. We have a report file, the GLHEPRO output file, the GLO file. Okay, so our first try, we got nearly 600 foot deep boreholes. Right, and you see our minimum temperature does occur in month 1, but it's 61 degrees, so it's not a problem. Right, this is a very cooling dominated building. Okay, so first of all, we're not going to be able to do 600 foot deep boreholes, or I'm going to assume that our drilling contractor is going to balk if we tell them it's 100 boreholes 600 feet deep. So there are several things that we might want to look at to try to improve the design. Right, we're pretty much stuck with the ground conditions. We could possibly go with a slightly higher temperature. Right, so maybe we just check that right now. So if we just went up to 95, right, then we drop down to 502 feet. So it makes actually quite a bit of difference. The problem is we'll have less cooling capacity at that point, which depends on your selection of your equipment. Also, our efficiency may, well, the cooling efficiency will be better if the temperatures are lower. So, and if you remember our sort of recommended starting point, 95 is more than 30 degrees higher. Not that much, but a little bit more than 30 degrees higher. So I think what I'd like to do is I'd like to stick with 90. Let's just see what else we can do. Okay, so we've got this solution. Okay, so the first thing I'm going to suggest is that our borehole design is not a particularly state-of-the-art one. So if we go back here, right, it may well be that if we use standard piping, right, this default value for the conductivity of HDPE is reasonably good, but this and the soil conductivity we're pretty much stuck with, but the grout conductivity, we could enhance that. Now, the approach I'm going to take is, in the early days, I think I mentioned one of the first thermally enhanced grouts is called Thermal Grout 85, if I remember right, but it had 0.85 conductivity. Calculate the borehole thermal resistance. You see how it dropped down to 0.25. Now, our borehole thermal resistance that we measure was 0.118, so it's still quite a bit better than that. And by the way, it is possible, for example, other things that happen besides that can affect the borehole resistance besides just changing the grout conductivity. So if the borehole diameter is larger than you think, or on average is larger than you think, that can make a difference. But let's just see what we can do to get the resistance down to 0.2048. So if we go to just 1.225, say 1.2, 0.2013. Right, ours was just a little bit higher than that. So if we can tweak this to match exactly. So I'm going to lower our grout conductivity a bit. Yeah, well, okay, I think we were 0.2042, so just say this is close enough. Okay, so let's just see what the effect is of putting a higher, better grout in. Calculate borehole resistance. Now we can size it. Okay, we've dropped down to 484.73 feet. All right, still probably deeper than most drillers can go to around here, at least on a regular basis. I know a few years ago, they drilled 400 feet deep to serve one of the engineering labs here on the OSU campus. Let's see, we might check to see, we'll probably get some benefit of spacing things out. So let's just check the impact of that. So down to 409. And now, could we do other things? Yes. But let's look at what happens if I think we might want to just try a larger borehole configuration. So let's go to 120. And really we should calculate the borehole thermal resistance. Okay, it's gotten just a little bit higher because our flow dropped a little bit. Okay, we'll just leave that. Okay, so now we're down to 332 feet. And it might be that if we go, to, oh, sorry, I lost my place where I'm going here. As I say, if we go just a little bit higher, like 92, right now we're down to 307 feet, so. Okay, so anyway, somewhere around 92, 93 degrees, we can probably get 120 boreholes around 300 feet deep. Now, there is more we could do. One thing I don't intend to do in this lecture is to use the hybrid sizing, although maybe this is a bad idea. This will actually allow us to size a system with a cooling tower, and it will, if everything works right, it will figure out what size we need. We'll see now we could get down our boreholes down to 71 feet, and we need a cooling tower capacity of around 700,000 BTUs per hour. Okay, maybe I'll have another lecture where I go into this in more detail. I only brought this up because it was, since we have 7.4 times, the cooling load 7.4 times the total heating load for the year. When we do a hybrid system, we can, what we're really trying to do is we're trying to, in our case, not absolutely balance the loads, but hit both the cooling and heating design temperatures. So we're adjusting the size and the operation to meet that. And So there's more than one possible hybrid sizing solution. We could size a different size cooling tower, right? But this would be a good example of a building where we might benefit from that. Okay, I think we'll stop here, and then I think we'll come back and just look a little bit some sensitivity to a few other things. So.